More than 2,000 years ago, Greek engineers built a hand-powered machine that could model the sky. It tracked the sun and moon, displayed calendar cycles, and predicted eclipses. Nothing else from the ancient world combined so many astronomical calculations inside one compact gear system. Today we call it the Antikythera Mechanism. Its story begins not in a workshop, but beneath the sea. In 1900, sponge divers sheltering near the Greek island of Antikythera discovered a Roman-era shipwreck. The wreck contained statues, luxury goods, and corroded bronze fragments that at first looked unremarkable. When the fragments began to split apart, traces of gear teeth appeared inside. Archaeologists realized they were looking at the remains of an ancient mechanical calculator. The mechanism probably sat inside a wooden case about the size of a small mantel clock. A user turned a handle on the side. That motion drove a network of bronze gears, moving pointers across dials on the front and back. The surviving fragments are incomplete, so every modern reconstruction contains some uncertainty. But the inscriptions, gear counts, and physical relationships preserve enough evidence to reveal the machine's main functions. On the front, a large circular display represented the yearly motion of the sun and moon. One ring followed the Egyptian calendar of 365 days. Another ring carried the 12 signs of the zodiac. As the handle turned, pointers moved across these scales, linking civil time with the apparent motion of objects in the sky. The moon required a more ingenious solution. Its apparent speed is not perfectly uniform because its orbit is not a perfect circle centered on Earth. The mechanism reproduced that variation with a pin and slot arrangement connected to gears. The result was a pointer that sped up and slowed down through the month. A small rotating sphere may also have shown the changing phases of the moon. This was not a clock that ran by itself. It was a model that advanced when someone turned the handle. By moving forward or backward through the calendar, the user could ask what the sky would look like on a chosen date. The machine translated cycles of time into mechanical motion. The back of the mechanism carried two large spiral displays. The upper spiral represented the metonic cycle, a period of 19 years in which lunar months and solar years returned to nearly the same relationship. Ancient calendars could use the cycle to keep months aligned with the seasons. A pointer followed the spiral through 235 lunar months. The lower spiral represented the Saros cycle, a period of a little more than 18 years that links repeating patterns of solar and lunar eclipses. Small inscriptions inside the cells indicated when an eclipse was expected, whether it would be solar or lunar, and sometimes additional characteristics. The mechanism did not predict an eclipse by observing the weather or the local horizon. It predicted recurring astronomical timing. A smaller dial may have tracked the 4-year cycle associated with major Greek athletic festivals. That detail reminds us that astronomy, calendars, religion, navigation, and public life were deeply connected. The mechanism was not only a scientific instrument. It organized several kinds of culturally important time. One of the most debated questions concerns the planets. Ancient Greek astronomers knew the irregular paths of Mercury, Venus, Mars, Jupiter, and Saturn against the stars. Inscriptions on the mechanism refer to planetary phenomena, and some researchers argue that the front display included pointers for all 5 visible planets. Physical evidence for the complete planetary gearing is limited because much of the mechanism is missing. Modern models can demonstrate how such a display might have worked, but they should be treated as informed reconstructions rather than fully preserved fact. The machine's complexity did not appear from nowhere. Greek mathematicians and astronomers had studied celestial cycles for centuries. Babylonian observations supplied long numerical records. Greek geometry supplied models of circular motion. Craftspeople supplied the precision needed to cut closely spaced bronze gear teeth. The Antikythera Mechanism brought those traditions together in a single object. Who built it remains unknown. Its date is usually placed in the 2nd or 1st century before the Common Era. Some scholars have connected its design with astronomical traditions associated with roads, while others have proposed different centers of manufacture. The ship itself carried goods from several regions, so the wreck does not provide a simple answer. Modern understanding advanced dramatically through imaging. X-rays first revealed hidden gears. Later computed tomography exposed inscriptions buried inside the corroded fragments and allowed researchers to count teeth that could not be seen from the surface. Each new scan changed the reconstruction. The mechanism became a scientific puzzle studied not only by archaeologists and historians, but also by engineers, astronomers, and computer modelers. What makes the device extraordinary is not a claim that it was a modern computer in the electronic sense. Its importance lies in the way it encoded knowledge. Gear ratios represented astronomical periods. Pointers turned numbers into visible motion. Dials allowed a user to explore dates, cycles, and predictions. It was a physical argument about how the heavens could be modeled. The surviving machine also changes the history of technology. Precision gearing is often associated with much later clocks, yet these fragments show that highly sophisticated gear trains existed in the ancient Mediterranean. The mechanism may not have been unique. It may be the only survivor of a broader tradition whose other examples were melted down, destroyed, or lost. Surviving written accounts also suggest that geared celestial models were known beyond this single wreck. Ancient authors described mechanical devices associated with celebrated mathematicians, although no complete example survives. Those accounts cannot prove a direct lineage, but they make the mechanism less isolated in its intellectual and technological setting. Even after more than a century of study, major questions remain. How exactly were the missing front displays arranged? Did the machine show every known planet? Was it made for teaching, calculation, prestige, or all three? How many similar devices once existed? Uncertainty is not a weakness in this story. It is part of what makes the mechanism scientifically valuable. The Antikythera mechanism survives as a set of damaged bronze fragments, but those fragments preserve a remarkable idea: the sky could be translated into a machine. By turning one handle, an ancient user could move through months and years, follow the moon, examine eclipse cycles, and connect human calendars with celestial motion. That is why this object still matters. It is not simply an ancient curiosity. It is evidence of a lost level of mechanical astronomy, recovered piece by piece from the sea. And every new fragment of understanding brings us closer to the world of the people who built it.